Okay, hello and welcome everyone. So I'm calling this video Simple Games. And what I'm going to do is I'll show 5 games. And for each of them, we're going to look to find each player's best responses. If there's any dominant strategies, any Nash Equilibria in pure strategies, we won't worry about mixed strategy Nash Equilibria. And then is the game a prisoner's dilemma? We'll talk about that. So, all right. First thing is I'm going to show all the games. That way, you know, maybe if you want to stop the video and take a look at them and try to solve them. But actually, I'll do an overview. Like I'll kind of talk about them first, but and then I'll show the solution. Okay, so first game, I'm envisioning this as being there's 2 players, and they're usually the way that I talk about this during lectures. You've got 2 players standing with their backs to each other, about 15 feet apart, and there's a table in front of both players. On one of the tables for one of the players, there's a basketball and a softball. And on the table in front of the other player, there's a glove. And they're going to turn around. And as they turn around, the player who's got the basketball or the softball is going to put the ball in the air. And the other person's going to prepare to catch it. Right? And because you're doing this at the same time, you can't go back and revise your strategy because you've already committed. And so the idea is, well, we've got 4 possible outcomes. You could toss the basketball, they try to catch with 2 hands. That works well. You could toss the softball, they try to catch with a glove. That works well. But we could also toss the basketball, they try to catch with a glove. Doesn't work as well. And toss the softball, they try to catch with 2 hands. Doesn't work as well. And so the payoffs are corresponding to the first number goes to my row player. The second number goes to the column player in all of these games. So for example, if the row player decides to toss the softball and the column player decides to catch with a glove, row player gets a 1, column player gets a 1. Right? Okay, so that's how the game works. What we want to do is find best responses, dominant strategy, Nash Equilibria, and prisoner's dilemma. Same for all of these. Okay, game 2. Now the strategies are just up, down for row player, picking going up or going down. For column player, choosing left or choosing right, referring to these 2 columns. The first number goes to the row player in all these cases as their payoffs for that particular strategy profile. The second number goes to column player. I've selected these kind of deliberately so that the odd numbers are always row player's payoff in game 2 and the even numbers are always column player's payoff. Game 3, suppose we've got coins. Could be pennies. This is matching pennies game. Could be quarters. Could be, I don't know, like dollar coins or whatever. If we're in Canada, they could be loonies or toonies, right? And so you could pick heads or you could pick tails. If you pick heads and your row player and column player also picks heads, you take their coin. Or if you pick tails as row player and column player picks tails, you take their coin. So if the faces match, row player gets the coin, column player loses the coin. If the faces don't match, then column player gets the coin. Then I've got another game, game 4. I'm calling this big little. So if both select big, then they each get a payoff of 5. If row player selects little and column player selects big, row player gets a 2, column player gets a 0. But if row player selects big and column player selects little, row player gets the 0 and column player gets the 2. If they both select little, they both get 1s. In the last game, Netflix and Hulu and Amazon Prime, you can think of 2 players. I don't know, maybe they're coworkers or whatever, and they're going to choose to watch the new series that's been released on Netflix or on Hulu, and they want to be able to talk about it, right? So do you watch the Netflix series or the Hulu series or the Amazon Prime, whatever. So if they both watch Netflix, turns out, I don't know, maybe row player likes the Netflix series a little bit better. Maybe it's Queen's Gambit or whatever. And that's now several years ago. Column player gets a payoff of 1. They're okay. Like they'd rather be able to talk about it with their friend, but it wasn't their favorite. They would rather watch the series on Hulu. And then row player, they get a positive payoff. They get to watch a series and talk about it with their friend, but they actually wanted to watch the Netflix one. Or maybe an intermediate preference that exists for row player only. Maybe they have an Amazon Prime subscription, so they could watch the new series on there. It's like Jack Ryan, the one with Jim from The Office, whatever. So, okay, so those are the games, and what we want to do is we want to find all players' best responses, find any dominant strategies, find all Nash Equilibria, and then determine, do you have a prisoner's dilemma? Okay, so I'm gonna now show the solution. Actually, I gotta scroll up so I can do this in order, and I'll walk through. What I've done is I've indicated best responses by what I call the underline method. So here's how you solve the game. I've got other videos that I'll link up. They're called like how to solve matrix games by the best response method. And I've got a couple other that do something kind of similar, but that's what we're going to do here. I'm not going to do it quite as deliberate in this video. I'm just going to do it with these underlines and explain where these are coming from. So even though these players are choosing simultaneously, which in game theory just means you're making your choice without knowing what your rival has done, they do know what they could do. So we're going to say, hypothetically, if column player is going to catch with two hands, and I know that, I would rather toss the basketball because then I get 1 rather than 0. So I've underlined the 1. Hypothetically, as row player, if I see column player is catching with a glove, I'd rather toss the softball because 1 is bigger than 0, right? I get a higher payoff than if I toss the basketball. Right, so I just underline the payoff that corresponds to my best response. Another way to say this is row player best responds to column player's choice of two hands by selecting basketball. And if column player selects catch with glove, row player best responds by selecting softball. If row player tosses the basketball, column player's best response is the catch with two hands because 1 is going to be better than 0. If row player has tossed a softball, column player is better off catching with a glove because 1 is bigger than 0. Nobody has a dominant strategy. Remember, dominant strategies don't like win the game or do better than the other player or anything like that. Dominant strategies dominate your own other alternatives. But that doesn't happen here because here each player's best response depends on what the rival has done, what the co-player has done. So there's no dominant strategies. There are Nash Equilibria. The two Nash Equilibria, if you have both payoffs underlined in a cell, right, then you've got a Nash Equilibria. So basketball and two hands is one Nash Equilibria, softball and glove is the other. Since they both lack dominant strategies, this is definitely not a prisoner's dilemma. It's a coordination game. Game 2, find player's best responses. So if column player selects left, row player best responds by playing down because 7 is bigger than 5. But if column player selects right, row player still best responds by selecting down because 3 is bigger than 1. If row player selects up, column player best responds by selecting right because 8 is bigger than 6. If row player selects down, column player best responds with right because 2 is bigger than 0. Since we've got underlines across both payoffs in column player's right column player has a dominant strategy to play right. And since we have underlines in both payoffs for row player's bottom row player has a dominant strategy to play down. You can have a Nash Equilibria where nobody has a dominant strategy. We found 2 of them right here. However, if somebody has a dominant strategy, that strategy must be part of any Nash Equilibria. And if they both have a dominant strategy, that'll pick out a unique Nash Equilibrium. In this case, it's down right. This is actually a prisoner's dilemma. Both have dominant strategies. And then also the other thing we've got to determine if it's a prisoner's dilemma is we look to see, are joint payoffs maximized when they play their non-dominant strategy? So when row player plays up and column player plays left, do they, between the two of them, sum their payoffs to something larger than they got in Nash Equilibrium? Sure. Because 5 plus 6 is 11, joint surplus is maximized when they play up left. Here it's actually minimized when they play down right. That's 5. Here it would be 9. Here it would be 7, right? That's why we say that prisoner's dilemma is a social dilemma, because the group incentive is for them to play up left, but that rests on non-dominant strategies. They have a very strong individual incentive to use their dominant strategy. They're not best responding if they choose up left. That's not a Nash Equilibria. Notice also the Nash Equilibria doesn't care anything about maximizing payoffs or whatever, right? Nash Equilibria is just defined as everybody's playing a best response, right? So nobody has a profitable unilateral deviation. All right, so game 3, if column player is showing the heads face of their coin, row player wants to play heads, so that's their best response because that's better to gain a coin than to lose a coin. If column player is playing tails, row player best responds with tails. If row player is playing heads, column player best responds with tails. And if row player is playing tails, column player best responds with heads because 1 is bigger than -1. There's no dominant strategies for the same reason as there wasn't in game 1. And there's no Nash Equilibria in peer strategies. There's actually a Nash Equilibria in mixed strategies. I've got a video that talks about finding mixed strategy Nash Equilibria. And I'll show like how to do that. Here, just intuitively, it's got to be the Nash Equilibria is each player plays heads and tails half the time. Because think about this. If you're row player and you notice that column player is playing heads and tails exactly half the time, you're going to go exactly half the time for yours also. But if you notice that column player seems to be playing heads kind of a lot, like 75% of the time, now all of a sudden you're going to start playing heads a lot, right? Because you're going to get 1 more often than you're getting -1 if you play heads. But that's not an equilibrium, because if you start playing heads a lot, now column player doesn't want to play heads as much. Now they want to start playing tails. But if you notice that column player is playing tails a lot, you're going to want to start playing tails a lot so that you can be down here. And it just cycles, right? So the only way that we get a stable point is if they're each playing heads and tails half the time. Is it a prisoner's dilemma? No. No dominant strategy, not a prisoner's dilemma. It's actually Matching Pennies is the name of that game. All right, so game 4. If column player is playing big, row player wants to play big as well because 5 is greater than 2. Right? If column player is playing little, row player best responds with little because 1 is bigger than 0. And then the game's symmetric, so it works the same. If row player is playing big, column player wants to play big because 5 is bigger than 2. If row player plays little, column player wants to play little because 1 is bigger than 0. 2 Nash Equilibria, no dominant strategies. It's another type of coordination game. So it's not a prisoner's dilemma. Big, big, and little, little are the Nash Equilibria in peer strategies. And then lastly, each player's best response for this, like, which series to watch game. If column player has selected Netflix, row player best responds by selecting Netflix because 3 is bigger than 2. If column player selects Hulu, row player best responds with Amazon Prime because 2 is bigger than 1. If row player selects Netflix, column player best responds with Netflix because 1 is bigger than 0. If row player is playing Hulu, column player is going to play Hulu because 3 is bigger than 0. And if row player selects Amazon Prime, column player is going to be indifferent between the two. They could play either. So I've underlined both. There's 2 Nash Equilibria. Maybe this Nash Equilibria is a little bit more convincing because column player is indifferent between these here. But in any rate, we've got 2 Nash Equilibria, Netflix, and Amazon Hulu. Is it a prisoner's dilemma? No, absolutely not. All right, so I'll go ahead and conclude here. I hope you enjoyed the video, and I'll see you in the next one.